Hello. So today we're going to be learning how to solve inclined planes. And the first step to any inclined plane problem is you're always going to want to draw your FBD first, or your free body diagram. And for an inclined plane, it's going to look like something like a right triangle. And we can mark this angle here as theta. And then we're going to have an object with a center of mass here. And today we're going to be working with objects at rest on inclined planes, assuming that the surface is not frictionless. So at rest, not frictionless. So then we can assume that you're going to have force of friction acting against the natural motion going this way. So we can draw a vector here, F. We are always going to have force of gravity, or Fg, acting directly towards the center of the Earth. So assume that this is the horizontal, then that's going to be the center of the Earth. And then we're obviously always going to have, unless we have an object suspended or static, we're always going to have a normal force acting from the surface to the box, pushing back up. Next, we're always going to have to resolve this free body diagram, because we need the forces to be acting in a maximum of 4 directions. And you want them always to be perpendicular to each other. So you want a maximum of force here, force here, force here, force here. It can be any amount of forces acting in each direction, but it has to be those directions for where we're at. So we're going to redraw the triangle. Right triangle. We're going to rewrite theta. This is the same angle. It might be not drawn to scale. But then, the difference that you'll notice, we're still going to have force of friction, and we're still going to have normal force, except we have to break up this vector into component vectors. And what component vectors look like, this is going to be the resultant, and the component vectors are going to be acting in this direction and this direction. So we can draw that in now. And in some other problems, you may have broken down forces applied at an angle into Fx and Fy. But writing Fx and Fy is wrong, because they're not acting along the natural x and y planes, because we're at an angle here. So it's not on a level plane. So what are we going to write it in relation to? Well, it's what we're going to be solving in relation to, which is the inclined plane. So this component vector is running parallel to the inclined plane. So we're going to write FG and then a parallel symbol. Excuse me. And then this is running parallel. Oh, I think I said parallel here. This is running perpendicular. And this is FG parallel. And it's going to be represented with 2 parallel lines like that. Now, if the object... we'll be deriving equations based on variables and universal constants. So, excuse me, you're gonna, FG parallel, we can derive a value for that. which can come in handy in actually solving problems. But we're going to be deriving equations, but FG parallel. And remember, these equations are specific to inclined plane equations. And so what that means is that it's not going to be applicable to every single type of problem. But we'll continue. FG parallel is going to equal to FG sine theta. And what this means is just showing that it's a component vector, whereas the original force, Fg, is the resultant between this force, and it would be going like that. Or, well, if you moved it tip to tail, then it would be going like that. All right. We can also write that Fg perpendicular is equal to Fg times the cosine of theta. Once again, it is another component vector, whereas this original Fg force is the resultant. And we can make a few assumptions based on this. So we can write, because the system is at rest, F net is going to equal to 0. And so the force in either direction, whether it be this direction or this direction, is also going to equal 0. So that's going to look like up minus down equals 0, because F net equals up minus down, and F net also equals right minus left. So knowing that, we can start deriving our equations. We can derive that, excuse me, we can derive that Fg parallel, or Fg sine theta at rest, is going to equal to force of friction. We can also write that in the absence of other forces, Fg perpendicular, or Fg cos theta, equals the normal force. And we can also derive the mu, or the coefficient of friction, of the surface acting on the box. And we can do that by writing mu Fn equals Ff. So then mu Fn, mu equals Ff over Fn. So now that we have our, we have three equations, and I just want to note that as theta increases, this coefficient and the force of friction, the normal force is going to decrease. And this is mainly because if you think about a real application, it's much easier to slide down something, so it's going to have less force acting upon it when it's a steeper slope rather than a flatter one. And that only applies increasing until 90 degrees. And then I just want to connect to some Newton's laws. So Newton's third law of motion says that for every action, there's an equal and opposite reaction. And these forces are known as Newtonian pairs. And this is applied where we see that at rest, FG sine theta, or FG parallel, and FF are equal because they're the same magnitude, and they're opposite because they're going in either direction. And that is what's known as a Newtonian pair. And also, Fn and Fg are also going to be known as Newtonian pairs. This is, we can also observe Newton's first law of inertia that says that an object will stay at rest because of, unless an uneven or unbalanced force is applied to it. And since we know that these are Newtonian pairs that are going to cancel out because the object is at rest and no force is being applied to it, there is no, there's no uneven force, so the box will not accelerate, it will not move up the slope, it won't move in the up or down direction because of its inertia, also known as Newton's first.